The ocean, a seemingly timeless and mysterious blue frontier, gave birth to the earliest life on Earth. Today, it remains the source of life on our planet, regulating the climate and providing food and resources. We think it is boundless and powerful, but not. Did you know that this magnificent ocean is facing an unprecedented crisis? It's not as violent as a typhoon or as visual as floating plastic trash, but it is profoundly and insidiously changing everything about the ocean. It is ocean acidification. Do you know what ocean acidification is? Do you understand what it means for our ecology and economy? More importantly, do we have the means to reverse this crisis? Today, we're going to explore these questions in depth and learn about a revolutionary technology, carbon capture and storage, and how it can help revitalize the oceans and save our future. When we talk about climate change, carbon dioxide emissions always seem to be in the spotlight. We often focus on its impact on global temperatures, but it's easy to overlook its deep connection to the oceans. In fact, about a quarter of the carbon dioxide we emit into the atmosphere each year is absorbed by the oceans. While this slows the greenhouse effect somewhat, it also triggers a more insidious but equally serious problem: ocean acidification. When carbon dioxide dissolves in seawater, it combines with water molecules to form carbonic acid. This carbonic acid breaks down further to release hydrogen ions, and the increase in hydrogen ions leads directly to an increase in the acidity of seawater, or a drop in pH. Over the past 200 years, the pH of the Earth's oceans has decreased by 0.1 units, a seemingly small change that actually means an increase in acidity of nearly 30%. The effects of ocean acidification on marine life are profound. For coral reefs, acidified water means that calcium carbonate, the material used to build the skeleton, is becoming increasingly difficult to obtain. We are seeing the bleaching and even death of large areas of coral, which are home to countless marine organisms, and their disappearance means the collapse of entire ecological chains. For shellfish and other crustaceans, acidification is a direct threat to their basic conditions of survival. Acidified water eats away at their shells, making them more vulnerable to predators. Even the reproduction and growth of fish are affected, as the acidic environment interferes with their sensory functions and physiological health. These changes are not just an ecological problem, but an economic one. Fisheries are an important source of protein for more than 3 billion people worldwide, as well as a source of livelihood for hundreds of millions more. With declining catches and imbalances in marine ecology, coastal communities are facing unprecedented challenges. This may sound like an irreversible crisis, but science hasn't stopped there. Through innovations in technology, we are finding new rays of hope for the ocean. The scientific community is not helpless in the face of the complex environmental problem of ocean acidification. Through breakthroughs in monitoring technology, innovations in carbon capture technology, and interdisciplinary collaboration, we are gradually building technological solutions to this crisis. Below, we explore in detail the current core technological tools from monitoring to action and, in particular, the important role of carbon capture and storage (CCS) and carbon capture and utilization (CCU) technologies. The first step in addressing ocean acidification is to fully understand how it occurs and develops. Scientists have established extensive monitoring networks to track trends in global ocean acidification. These monitoring networks rely on a range of advanced equipment and techniques. Modern pH sensors can accurately measure changes in the acidity of seawater. Scientists mount these sensors on buoys, seafloor stations, and unmanned underwater vehicles to collect real-time acidification data from shallow to deep water. For example, with thousands of automated buoys deployed around the world, the Argo project is able to provide detailed water analysis data every few days, including changes in temperature, salinity, and pH. This real-time data not only shows the current status of ocean acidification, but also helps predict future trends. The amount of data generated in marine research is growing rapidly as monitoring technologies are upgraded. To effectively utilize this data, scientists have introduced artificial intelligence and machine learning technique. AI systems are able to identify implicit patterns in massive amounts of data, spot hotspots of ocean acidification, and predict ecosystems that may be severely impacted. For example, combining historical data and real-time observations, the AI models were able to deduce which coral reefs were likely to bleach in the next decade due to acidification, helping scientists prioritize the most vulnerable areas for protection. In addition to chemical monitoring, scientists are also using biological indicators to assess the impact of acidification on marine life. For example, the severity of acidification can be visualized by observing changes in the growth of corals, shellfish, and plankton. This combination of biology and chemistry provides an important basis for developing conservation strategy. If monitoring is the first step in identifying the problem, then carbon capture and storage (CCS) technology is one of the most important means of slowing down ocean acidification. The core objective of CCS technology is to reduce the amount of carbon dioxide entering the atmosphere and ocean at the source. CCS technology is primarily used in industrial processes where fossil fuels are burned, such as coal-fired power plants and oil refineries. It works in the following steps. Capture. Separating the emitted CO2 from the industrial stack. This step is usually performed using chemical absorbents, such as amines, which are highly effective in capturing CO2 from the flue gas. Compression and transportation. The captured CO2 is compressed into a liquid state and then transported by pipeline or shipped to a storage site. Storage. Liquid carbon dioxide is injected into deep geological formations such as saline aquifers, depleted oil fields, or natural gas fields. These sites have been scientifically evaluated to safely sequester CO2 for long periods of time to avoid leakage. Currently, there are several successfully operating CCS projects around the world. For example, Norway's Sleipner project is the world's first large-scale carbon dioxide storage project and, since 1996, has sequestered more than 16 million tons of carbon dioxide. The Boundary Dam project in Canada has reduced power plant emissions by more than 90% through CCS. These projects not only demonstrate the feasibility of CCS technology, but also provide important lessons for future improvements. However, the main challenges facing CCS technology are the high cost and the difficulty of scaling up. With technological advancement and policy support, these bottlenecks are expected to be gradually overcome. In contrast to CCS technology, which seals carbon dioxide underground, carbon capture and utilization (CCU) technology focuses more on how to convert captured carbon dioxide into valuable products. This technology not only reduces carbon emissions, but also creates new economic opportunities and is an important part of realizing a circular economy. Main application areas of CCU. Building materials. Captured CO2 can be reacted with minerals to produce calcium carbonate, which can be used to make concrete and other building materials. This carbonized concrete is not only stronger, but also locks in the CO2 permanently. Chemicals. Carbon dioxide can be used as a raw material to synthesize chemicals such as methanol and plastics. For example, through a catalytic reaction, CO2 can be converted into methanol, an important industrial fuel and chemical feedstock. Agriculture and food. Captured CO2 can also be used for greenhouse farming, providing additional CO2 for crop photosynthesis and increasing yields. In addition, carbonated beverage bubbles used in the food industry can also come from CCU technology. Advantages of CCU technology. Compared with CCS technology, CCU technology can directly create economic value and is therefore more readily accepted by the market. For example, a chemical company in Germany has already converted CO2 into polyurethane foam for mattresses and furniture through CCU technology. This technology both reduces the use of petrochemical raw materials and increases the profitability of the company. Although CCU technology is mature in technical principle, it still needs to overcome cost and energy efficiency issues to realize large-scale application. For example, the chemical conversion process of carbon dioxide usually requires high energy consumption, so more efficient catalysts and reaction units need to be developed. In the future, as green energy becomes more widespread and technology is optimized, CCU technology is expected to become an important complementary solution to combat ocean acidification. While advances in carbon capture technology are encouraging, the technology alone is not sufficient to fully address ocean acidification. Global policy support, financial investment, and public awareness are key to promoting the large-scale application of these technologies. Policy support. Governments can incentivize companies to adopt CCS and CCU technologies through policy measures such as carbon taxes and emissions reduction targets. At the same time, international cooperation is particularly important to promote these technologies, especially in developing countries. Public participation. Raising public awareness of ocean acidification and carbon capture technologies will help to promote their widespread adoption. For example, educational programs can help students understand the principles and potential of these technologies so that they can become supporters and practitioners of their development in the future. By combining technology with action, we can not only slow ocean acidification, but also pave the way for achieving the global sustainable development goals. It is a challenging but promising future. These technologies are in a phase of rapid development. Despite the challenges of cost and scale, through international cooperation and policy support, they are expected to be applied on a large scale in the coming decades as an important tool in the fight against ocean acidification. In the face of such a complex crisis, technology alone is not enough. Policymakers around the globe are promoting national emissions reduction targets by pushing for international agreements such as the Paris Agreement. At the same time, increased investment in green energy and low-carbon technologies is an important part of the solution. Everyone can be part of the solution, from choosing renewable energy to reducing plastic waste to promoting community environmental initiatives. Every small action can contribute to the future of the planet. Ocean acidification is an unprecedented crisis, but it is not irreversible. Through technological innovation, policy support, and the efforts of everyone, we can bring this ocean back to life. Imagine a vibrant future. Healthy coral reefs, abundant fish stocks, balanced ecosystems, a goal we all share and a hope worth working for. The future is not doomed, so let's take action and start now to write a new chapter for the oceans together.